Alright, so let us begin with some prerequisites for the topic of vector space. When you see the definition of vector space, you'll find it requires some basic understanding of groups and fields. And when you go for groups, you'll find you need some basic understanding of sets, right? So we'll discuss these things, that is sets, groups and fields, in a bit. Algebra. Okay, so let's begin with some prerequisites for the topic of vector space. When you see the definition of vector space, you'll find that it depends, it requires some information, some basic understanding of groups and fields. And when you go for groups, you'll find it requires some basic understanding of sets. It means it's sort of linking chain, right? No issues. What we will do, we'll study some brief, that is just an introduction of things, right? Not even introduction. Only some few things which are useful for us now. Definitely, I'm going to discuss groups, rings, and fields in detail because we have one topic in paper 2. If you noticed, that is modern algebra, right? We have it there. Okay, so let's begin with sets. Set is actually collection of some well-defined things. And if you have some well-defined definitions. Definition, why I'm saying? Because there may be definitions like most intelligent people, most efficient person, right? So those definitions are, when you look at broad aspect, you'll find these are vague definitions. Because if I'm saying that, okay, I'm intelligent in mathematics, then somebody will ask me to kind of write some poem, then I'll be like Tantan Gopal, nothing. Okay. Oh, one thing I want to check whether I'm talking in English, right? And I know that my English is poor. That's why I keep on getting stuck in between, searching for vocabulary, etc. But I think this is one of the means of communication here, and apart from this I can communicate in Hindi also. So if you think that I need to kind of include Hindi as well, so just let me know in comment so that I can improve from next session. Alright, so okay, thanks for that, and let's continue with the sets. So it is a collection of well-defined things. Let's say if I'm saying collection of all integers, so definitely it's going to be a set because it is universally accepted that what are integers, right? If you are saying, okay, -1 is a natural number, somebody will say you need to read a bit more, because it is universally accepted that -1 is not a natural number. So natural number start from 1, so it's this 1, 2, 3 and so on, this way. Okay, now you can notice one thing. These natural numbers are actually, we can find in real numbers also. So when this thing happens, then we say that Z and N have some relation, and that is N is a subset of Z. Okay, N is a subset of Z. Now if suppose we are provided with 2, and we can see clearly that it is in N as well as in Z also. So we say, okay, 2 is belonging to N, and 2 is also belonging to Z, right? Think about -3. Can we say it is belonging to N, that is set of natural numbers? Definitely no, because natural number cannot be negative, right? But for sure we can say, okay, -3 is there in Z. So subset, whether particular element belongs to a set or not, that thing. These are few basic things. We have already gone through these things in 11th standard. So I guess we should not waste time here. Let's move further to check the other things also. Think of two different sets. Let's say A, which is 1, 2 and 3, and B, which is another set, let's say it is 2, 3, 3 and 4, 3 and 4. Alright. Think of if I am subtracting set A, that is set B from A. So what should be the answer? In this particular case, what we do, we kick off those elements which are common, right? Kick off those elements from A actually, which are common in A and B. So here 2 and 3 are common. So it means it remains with this, right? So it is A minus B. Now think of B minus A. Somebody must be thinking that, okay, if A minus B is 1, then B minus B is also 1. But that's not true. Because when you need, now this time you need to kick off common element from B set. So what are common is 2 and 3. When you're kicking off those elements, it means you are left with 4. So it's different. Alright. Now if I'm taking another set C, which is say 1, 2, and I'm saying what is C minus A, what do you think? We have only 2 elements in C which are common with A, and we need to kick off these elements. So it means we are left with nothing. This kind of set where no element is found, we say it is null set. Phi. Okay, it is null set. So starting from here, we can now jump to the union and intersection of two sets. Let's think about union. So A union B. Here we keep the common element as well as the uncommon element. We do not count common element twice, right? So it's 1 which is uncommon, then 2 and 3 are common, then 4 which is uncommon, right? If you want to represent this, if you want to see it visually, then use the Venn diagram. Suppose this is A, right? Then think of another set. Let's say it is B here. So it's 2 and 3 are common, right? So make 2 and 3 in this common region. Here you can represent 4 and use the same color to represent 1 here. So when you are saying union, it means we are thinking of the entire region here, right? This entire region. Okay, it means all the elements of A and B and the common. Now let's think of intersection. A intersection B. What do you think? Intersection means this common section only. So the common section, you can find this common section is actually having 2 and 3 there, right? So that's 2 and 3. It's going to be 2, 3. This is the only common part. So it is A intersection B. Alright. Now if you noticed, I just want to give you the information of one property of a relation. So see that A, the set A, right, is a subset of N. You can see the element 1, 2, 3 are there. You can see, right? So we can say, okay, A is a subset of N. And we already seen that N is a subset of Z. Then we say A is going to be a subset of Z, right? Now quickly tell me what this property is called. This is called the transitive property, right? So when we are talking about relations from one set to another set, those relations are basically the need of why we are studying the set, because those relations are required in groups. Okay, so those relations, this particular property called transitive property of that relation. You can simply think of A is equal to B, B is equal to C, then A is equal to C. Alright, so this equal to relation, it is what? It is transitive in this particular way. Alright. Okay, so this is some basic things about set. Now let's study some basic things about groups and fields. Okay, so let's jump to the groups. And don't worry, if you need some detailing on set theory, just let me know in comment, right, so that I can make a full-fledged video on set theory, right. I'll discuss each and every aspect of set theory, Venn diagram, other operations, right, and all the relations, basically, on entire properties, that is reflexive, symmetric, and transitive, those things, everything I'll discuss, right. Just let me know whether you need it or not. Group. So group is what? Group is basically, it is a set, whether a set is forming a group or not. This is what we need to do. So it is a set actually. Let's say we have set A, and we need to check whether it is a group or not on a particular given operation star. What is it? It is the operation, right? So if it is a group, we say okay, then it is going to be not this way, it is this comma star. It is going to be the group. We represent it this way. Alright, if it is a group. If not, then we leave it. So what is the condition for A being group with respect to this star operation? So 4 things are given actually. What we need to take care. First, it must follow the closure law, right? So it must follow the closure law. What I mean by closure law? Sorry. What do we mean by closure law? Closure means that if we are taking any 2 element from A, right, any 2 element from A, and we are applying the operation. So when we are applying operation, it means definitely the operation will result into another thing, right? This, let's say it's C. So this C must also belong to A. This is what we call closure operation. For example, you can think, suppose we have 1, 2, what are these? These are belonging to Z, integers. Now let's apply this plus operation. This is an operation. 1 plus 2, it is 3. Think, it is also in Z. You can find it, right? So it means this Z, the set of integers, is what? It is closer, I mean, with respect to this plus operation. Alright, addition operation, that is. Alright, so it is a closure property. Then we have another thing, that is, it must be associative, right? Associative. I hope the spelling is correct. Or associative property, whatever you call, right? It says that if you can choose 3 elements from our set A, right, and we are applying this operation, then it must not be dependent on the order of application, right? Whether you are applying this on B and C first, then applying to A, or when you applying between A and B and then you applying C, right? It should not kind of bother. It should be same. This is what the associative law. Alright. Third thing is existence of identity. Existence of identity. Identity means, suppose we are talking about with respect to this plus, what is the identity? Identity means if you are applying operation between one element and the identity, then that element returns back. There is no change. Suppose we have taken A from our set, and let we have some E element there in our set, such that operation star on E is irrespective what we are doing here, because I mean irrespective means whether it is committing or not, it should be it's not capital. Capital is the complete set, sorry. So it's going to A. There is no impact on the element on which between E and A we are taking the star operation. Sorry, star operation. My throat is creating a bit problem, so I'm sorry for that. Alright, so it means this E is what? E is identity. Now let's look here. Suppose we are talking about Z and this plus. right? If I'm taking 1 plus 0, right, it means I'll get 1. It means this is what additive identity here. Now if we change the operation, let's say dot, then if I'm saying, let's say 2 into, that is dot 1, then it's going to represent 2. I mean, that's going to return 2. So you noticed, in case of addition, what we have 0 as the additive identity, but in case of multiplication you have 1 as the identity, that is a multiplicative identity. So identity keeps changing. Similarly, inverse keeps on changing, it depends on the operation. Alright, now let's discuss the fourth one, that is the existence of inverse. Existence of inverse. So what is this inverse means? Inverse means when it is when we are applying the operation between inverse and the element, then we are getting the identity, right? So let we have A and some A P, let's say. It is these two things are belonging to our set in such a way that when we are applying the operation here AP, we are getting identity element as the result. Alright, so then we say that AP is the inverse of A with respect to star operation, right? It's not true that always you are going to get the same thing. Like here, this particular dot, when you're applying the inverse, will you be able to find? No, that's why it is with respect to dot, it's not a group, because we know that this 1 is the identity element. So if I want this to dot with something x, I should get 1. It means my x should be what? X must be half, which is not a part of z. It is a real number, it's not a part of z. It means with respect to dot operation, z is not forming a group. Alright, so if we want, if we are looking for a set to kind of whether it is forming a group or not, then we need to with respect to the particular operation, we need to check all these 4 properties. If they are holding, then it is a group. If they are not holding, then it is not a group. And along with these 4 properties, if we have another property holding, that's a plus point. Fifth one we call as commutative property, right? Commutative property. If it is holding true, when you can say commutative law, then what happens? The group becomes abelian group. What is commutative? Suppose you got A comma B there in our set, such that you're having A star B is same as B star A, then we say it is abelian. So up to these 4, if up to these 4 are satisfied, then we say it is a group. Till here, what we say? It is a group. So we represent A comma star this way. But when you got this 5th property also satisfied, remember, along with previous 4, this 5th is satisfied, then you say that it is an abelian group, right? So A is an abelian group. It's E, abelian group, right? Definitely with respect to what? Star. Okay, so this is going to form an abelian group now. All right, here I'm leaving with this group particular topic. Now moving to fields, because group definitely we're going to discuss in detail in this modern algebra particular things, right? And let's discuss field. What is a field? But before field we need to check ring. So field is nothing but a commutative ring actually, right? Division commutative ring. So what is a ring? Like in case of groups, we had only one operation, but in case of ring or fields we have 2 operations. Okay, so I'm discussing directly this field itself, right? Leaving the ring field. So if we have a set, let's say A, and we want to check whether it is a field or not, then it should be kind of with addition and with dot, it should be following all the properties which we have discussed already. All right, so if it is forming a field, then the previous properties, that is this closure, associative, existence of identity, existence of inverse, those things we should check, right? It must be followed. If it is followed, right, then it is done. And also the commutative, all the 5 commutative also, then it is a field, right? And these properties must be satisfied individually with plus and dot, right? So I'm writing those all plus 5 properties and then some remaining points. So all above 5 properties with respect to plus and dot, right? Plus, a big plus means apart from these properties we should have few more things, right? So that is distributive law. Distributive law. Right? It should be distributive law over, that is dot over plus, this way. It means if we have A, B, C belonging to A, then it should have right and left distribution also. Alright, right and left. So left means okay, let's discuss right first. Let's say A plus B, from right you have this dot with C, so it should go A dot C plus B dot C. Then the left one, that is, let's say A dot B plus C, right? So you should get A dot B plus A dot C, right, this way. It is what? The distributive law. Alright, so these things we are going to discuss in detail in the modern algebra, but for now, as we need some basic understanding of groups and fields to begin with vector spaces, that's why I discussed this. So till here we have done the understanding of geometrical and matrix representation, basically row or column vectors. Then we have discussed a bit about sets, and then groups and fields. All right, so these are basically some prerequisites for to begin with the vector space. In next session we are going to discuss vector space, and I'll try to kind of cover up to the level so that we can begin with questions from next session or next to next session. All right, see you then, take care, bye bye.